Okay, let's begin. Thank you everyone for joining our latest session in our global webinar series. Today's topic is aluminum electrolytic capacitors for automotive applications. My name is Wilmer Compagnon and I'll be hosting today's webinar. So without further ado, I'll hand it off to our presenter of the day, Austin Finley from the Aluminum Electrolytics Business Group, and he'll be talking to us about some of the advances in our aluminum electrolytic offering that makes them suitable for automotive applications. So Austin, the floor is yours, my friend.
Thank you very much, Wilmer. Good morning or good afternoon, depending on when you are watching this, everyone. And like Wilmer said, we will be talking today about aluminum electrolytic capacitors for automotive applications. Now, as he said, my name is Austin Finley, and I am a technical product manager for the electrolytics business unit here at KEMET. I've now been at KEMET for 4.5 years, started as a process engineer and have transitioned into this technical product manager role. If you have any options for an electrolytic capacitor going forward, you can see my email there, and you are feel free to reach out to me at any point. So with KEMET's axial and radial crown capacitors, we offer a wide variety and range of voltages and capacitance values. Our largest series, as far as ranges go, is our commercial series of the PEG 124. You can see those go up to 450 volts and up around 5,000 microfarads of capacitance. Our AEC Q200 series are the PEG 127, the 220, 225, 226, and then the product we'll be highlighting most today, the PEG 236, which does offer temperature up to 165 degrees C. Now, different applications that are more typical for our axial capacitors are your cooling fans, your power steering, water cooling pumps, braking and injection systems, and most often as a DC link capacitor to help compensate for the inductance, operate as a local energy source, and limit the electromagnetic interference. One of our most recent applications has been inside the 48 volt inverter for a mild hybrid electric vehicle. So KEMET's majority of the axial capacitor lineup at the 105C range, you can see our PEG 124. However, if you wanted a longer life capacitor, you would look at the PEG 130. And both of those are more general purpose parts. At the 125C level, there's the PEG 124. But if you wanted a increased vibration rating, you would look at the PEG 225, and the 225 is AEC Q200 versus the general purpose for the 124. And at the 150C range, we have the PEG 127. But if you wanted more ripple current out of that part, you would look at the PEG 226. And now, with our most recent release would be our PEG 236, which is a 165 degrees C capacitor, and KEMET is the first to market on this. So the main features of this 236 part is obviously the 165C rating. It is also AEC Q200 qualified. We have very high ripple current rating up to 22 amps RMS at 140 degrees C, and a vibration resistance up to 20 G. Now with the table in the upper right, you can see the different dimensions that we offer at various capacitance values in either 25 volts or 40 volts. But I really want to draw your attention to the lower right-hand corner graph. And what you'll see is, we have that 1,000-hour rating at 165C, but as you lower the temperature, you can see that the parts dramatically increase in life. So approximately every 10 degrees C drop in operating temperature, then you can double the life of the capacitor. And this is definitely focused towards the automotive market segment, looking at power steering, transmission, like we discussed before. Now in the upper left, you can see the typical construction of an axial capacitor. And what makes the PEG 236 different is that there's a unique paper and electrolyte combination which improves the performance of these parts, giving that lifetime of 1,000 hours at 165 C. In the upper right, what you can see is the change in capacitance value and ESR for a life test of this part with a ripple current of 14 amps. The capacitance drops very little, and the ESR also increases just very marginally and well within our specified limits in the data sheet. Now with the lower right graph, what we're comparing here is different dimensions of capacitors from the 226 series to the 236 series. And what you can see with the 236 series is you can get a lot more ripple current compared to the 226 series, and approximately 2.5 times at 150 degrees C. Here is a preliminary specification for the PEG 236 series, and what I want to highlight is at 25 volts we're offering a capacitance up to 2,000 microfarads, and with the 40 volt part we can offer up to 640 microfarads currently. And you'll see in the middle the ripple current ratings. All of these ripple current ratings are with the capacitor heat sinked. These graphs here give a 25 volt and a 40 volt part, and what it really shows is across frequencies from 1 to 100 kilohertz, the ESR remains very stable. And you can also see how much the ESR drops as the temperature increases on both graphs. With the AEC Q200 tests, we're really showing how much this 236 part has survived, whether it be endurance testing, temperature cycling, surge voltage. We've really put these parts through the ringer and they've done nothing but shine. Here's a little more detail about the endurance life test. Same thing I pointed out before. In the upper right corner graph, you can see that there is minimal cap drop after 1,000 hours of testing. And then in the lower right graph, you can see the very minimal ESR increase after the 1,000-hour testing. Now, one thing I will say, the end of life criteria for the cap shift, you can see it on the upper right graph. It is a 15% shift, and the ESR change is 200% of the ESR limit, or 2 times the ESR limit. Now this next test that we were performing is using our ripple current tester. And if you look at the image on the right, you can see that we're able to get core temperature of the part, we can get the case temperature of the part, and this chamber allows us to heat sink the parts properly. So the setup of this test was to heat sink the parts, apply a ripple current of 14 amps at 10 kilohertz with a 14 volt bus. The capacitor's mean hotspot temperature got up to the 165 C rating. And you can see after 1,000 hours, the change in cap was only approximately 5%, and the ESR at 100 kilohertz only increased approximately 7%. And at this point, I want to change screens. So if you don't mind giving me 1 second, we're going to go check out KEMET's Web Life Calculator. So on our website at elc.kemet.com, what we have is an aluminum electrolytic capacitor life expectancy calculator. So I've thrown one example in here of the 236 series. It's a 1200 microfarad part at 25 volts. And the operating conditions that I've put in is, let's say that you want to, that your circuit at 75% of the time has an ambient temperature of 105 C at 25 volts and 1.5 amps of ripple current at 10,000 hertz. But at 25% of the time, that ambient temperature increases to 165 and the operating voltage still at 25 volts and your ripple current at 1.5. So if we do hit the calculate button, we see that it gives an aggregate life of 2.8 thousand hours or 2,800 hours of life. Now, one thing we encourage with aluminum electrolytic parts is to heat sink them. So let's say if we change this natural convection to heat sink, and we still keep this temperature right around that 105 C mark, say you're using coolant in the 100 C range, that doesn't bring it down too much. But what it does do is have a big impact on the temperature over here, where we change this to heat sink and say that brings the case temperature from 160 to 150 C. Now we hit calculate again, and you've more than doubled your life just by heat sinking this part and helping bring that case temperature down. So what I'll end with is just a quick recap, just a reminder, KEMET is the first to market with these 165°C rated parts. The AEC Q200 qualification is finalized and approved for the PEG 236 series, and we are currently offering voltages of 25 volts and 40 volts for this product. Thank you very much, and I will hand it back over to Wilmer.
Thank you, Austin. It took me a second to get myself unmuted here.
No worries.
So yeah, if you have any questions, please submit them through the Q&A portion of the Zoom window. And Austin, actually, I do have a question. Now, you mentioned heat sinking, and you showed in electrolytic life calculator that I think it was just 15 degrees of additional cooling you can get. What is it? Over double the expected hours. Do you have any guidance as to when and how we should be applying heat sinking?
Honestly, no. I think that, is customer specific, whether it be what sort of board space they have available, what sort of compartment space they have available. I think heat sinking can look different for different customers.
Okay. Yeah, I suspect maybe trace width and length, anything to try to of course get some heat out of the component, even if it's via the leads.
Correct. Forced air cooling, things like that. Any little bit helps.
Okay. And the next question I have is, do we have any guidance or any information on vibration performance for these things? Because yeah, we're talking about automotive applications where it's not exactly a friendly environment. So do you have any sense of that?
So currently the parts are qualified at 20 G per the AEC Q200 qualification testing. And that does assume that the part has been clamped by the body, whether it be, I think we have several customers that do RTV, things like that, to make sure that the parts are not moving.
Okay.
Because that vibration rating is for the wound element inside of the can.
Yeah, can you elaborate on that a little bit, Austin, about why it's significant to make a distinction in being clamped by the body, uh, and what happens to the wound element inside?
Correct. Yes. So what happens is that wound element can, if not clamped by the body, then the main concern is actually the leads on the outside. If the part is not clamped by the body, then the part can swing all over the place and you run the risk of breaking the leads. Whereas if you clamp by the body, the wound element is designed such that it fills up as much of the can as possible. And there's actually a groove that is in the center of the can itself, and that really helps hold the wound element in place.
Right, and that is, as I understand it, meant to prevent the wound element from actually becoming detached internally, right?
Correct. So there are tabs that are attached to the wound element, which then attach to the capacitor body on the inside or the lead. And that's what we're really trying to protect.
Okay. And a little bit back to the heat sinking question, it's interesting you mentioned forced air. You Do you have any guidance or recommendation? Is forced air versus actual, heat sinking using a solid metal body to put the heat sink into?
Uh,
Any
uh,
sense of like maybe which is better, or is it? Um,
I don't think that one is any better than the other.
okay.
Not that I've seen. It's the main goal is just how much heat can you remove from that capacitor body?
Got it. The next question here is there any shock testing done? I guess there's like shock impulse rather than just static, like vibration.
I am not. Let me do a double check before I speak out of turn. Not that I am aware of. I don't think there's any real full-on shock testing, but you know, it's not out of the realm of possibility to do if there's a special customer requirement with the right volume, things like that. But
Yeah,
as far as a standard practice, I don't know that it is for an AEC Q200 qual.
yeah. I guess we have the capability. It's a matter of is it a sensible thing to do based on the specific opportunity and need?
Correct.
Yeah. All right. Um, there was a mention here on that there appeared to be a gap in coverage of the capacitors. If there's they're referencing here page 3. So can you quickly go to page 3, Austin?
Yes, I'm there.
Well,
So,
you're not sharing
sorry,
your screen. Yeah.
that would probably help. So I
So
assume the gap is this gap here is what we're referring to, the gap
yeah,
in coverage.
that's what it must be. So what's any options to potentially cover that middle gap, or why?
So
What?
I think the graph kind of makes it disproportionately show that we don't have any offerings. If you look at the 225 and 226 series, we do offer up to 80 volts, and the PEG 124 covers 100 volts. So we don't see a lot of application voltages that require your quote unquote 90 volt rated parts. So that's just not an area we've pursued.
Yeah, I guess it's one of those. It's not necessarily a continuous spectrum of voltages and capacitances.
Correct.
Yeah.
And it just shows a little more on the voltage side of the graph.
Yeah. All right. Well, if there are no more questions, I think that's it. I'd like to thank everybody for attending. Thank you, Austin, for putting all this together. And we look forward to seeing you on a future KEMET Global Webinar, and we'll have one next Tuesday. So thank you very much for attending, and thank you, Austin, and we'll see you next time.
Thank you, Wilmer.